uh, when it comes to permanent deformation, so the shape will not come back to its original uh, shape and size. Okay, so that is a permanent deformation. Deformation means it is losing its shape and size or its form. Okay, form it also in simple words it is nothing but it is the shape and size. Okay, so this is what you learn. So elasticity, there are two things. One is plastic and then elastic. Okay. So we'll be more interested on elastic materials than the plastic materials. Plastic is also useful, but for our discussion, we'll more focus on the elastic material. Okay. So what are the examples for plastic? Plastic, you can take mud, putty, and all those. So those are the examples for your plastic material. And when it comes to elastic material, so if you take your quartz is the one of the good elastic material. Then you also have rubber and polythene. So you have different types of materials, even metals. Okay, even if you take stainless steel, it is also having some elastic property. Okay, that means you apply pressure on the steel rod or steel bar, and if you don't cross the limit, then what happens? Something called as elastic limit that you will come to know later. Okay. Then what happens? If you remove the applied load, then your stainless steel rod or your bar will come back to its original shape and or it is form. It will get its original form. So that is your elastic. Okay. So now there are three main things that you need to know. One is first one is your load. Load is nothing but it is your external applied field or deforming field. You can also call it as deforming field. Okay. So the external field or the deforming field or the force that you apply. Okay. Deforming force that you apply is nothing but it is your uh, uh, load. Okay. Deforming force. I will put as deforming force is nothing but your external applied field, applied force, which is called as load. Okay. Then what is the stress? So once you apply some force, external force, the material, for example, if you are taking a rubber rod or even if you are taking a stainless steel rod, this is stainless steel rod uh, will exert some force on the applied field. Okay, so that is what we call as internal restoring force. Restoring means it wants to come back to its original shape and size. Okay, so that is the what we call as a stress. Okay. Stress is normally given as force by area. Okay, so force by area is your stress. So this is the SI unit will be Newton per meter square, or you can also use the pascals. Okay. Then the strain. What is strain? So once you apply the load and there is a stress, this too would result in what we call as a strain. Strain is nothing but once you remove the applied field. So if there is any change in its dimension, then that we call the ratio of change in dimension to the original dimension, we call it as a strain. Okay. So if it is perfectly elastic, then what happens? Strain is almost zero, or it is almost zero. But there is nothing called as perfectly elastic or perfectly plastic. Okay. So you will have some kind of strain always in your in these materials. Okay. So this is your strain, and then based on the uh, what kind of force you are applying, you can again have different kinds of stress and different kinds of strain. Okay. So the stress is many types, but basic, like very basic thing, we can have it as longitudinal or linear or stress. Okay. Then the second one is your tangential or shearing stress. The last one is volume or bulk stress. Okay. I explained this is like one dimensional stress, then this is a two-dimensional stress, and then this is a three-dimensional stress. Okay, so the reason is, so in the first case, if you take a material which is having one of your the dimension is very large compared to other two. Okay, so if I take a scale, what happens is scale is very long, and then what happens, your the width is very less, and even the thickness is very small. Okay, so if I take 1 meter scale, then This may be like 2 centimeter, okay, or 2.5 centimeter, almost 1 inch, okay. 2.5 centimeter, and then the width, okay. Then the thickness may be like 1 millimeter, okay, to 1 mm. So in this case, what happens? These two are very very small compared to your length. Okay, so length is very large. So in this case, if I apply the some force, what I will do is I'll put a clamp here, and I can fix this one end. Okay, one end I'm going to fix it. Then I'll put a clamp and I'll start pulling this out. Okay, so in this case, what happens? There will be a change in length. So the change in length is more compared to in width or the thickness. Okay, so in that case, we are going to ignore any changes in this case. Okay, so there will be change. We don't say there is no change, but this is almost ignored because this will be very very small. Okay, so in this case, what happens? You have stress in only one dimension. So this is what we call as the longitudinal. Okay, so longitudinal stress is the force per unit area, but in a one dimension. Okay, so that is your longitudinal stress. Then what happened in case of your tangential or shear stress? So this two dimension. Two dimension means, so in this case, you are fixing this bottom here. Okay, so this end is fixed. Then what you are going to do is you are going to push this up layer. Okay, so the dotted one is the original shape. So once you push this from the upper layer, what happens is there the bottom layer cannot move because this is fixed. Only the upper layer is going to move. So in this case, what happens? The length is going to change. At the same time, this there is some small change in the shift. Okay, or small change in this width. Okay, so then this becomes like a two-dimensional change. So this is like a shearing stress. Okay, so normally when you have this shearing, there is a shearing angle, what we theta. So theta is nothing but it is the angle between these two, or the angle made by this triangle. Okay, the last one is your volume. This I told it is a three dimension. So if I take cube, this is the better example because then you can realize three dimensions. Okay, so there is this is having some certain width. Okay, so this is your, if I take, this is your width and this is your height, and then the last one which is in your z direction is your thickness. Okay, so all three are almost same. If or length into breadth into height, you can write anything, but I'm just taking this is like so I will call this as length. Okay, length, height, and width. Okay, width, or this is a thickness. Okay, so now what happens? All three are almost having the same dimension. So in this case, you have to apply uniform field from all six directions. Okay, you cannot apply some force in one direction. You cannot leave the other end. Okay, so you're going to try to apply force. It can be compressive force or expansion force. Okay, so in this case, it is a compressive force. That means you're trying to squeeze this uh, square. Okay, so from all the uniform force. So from all six sides, you are applying a uniform force. So in that case, what happens? There will be uniform displacement of the on all the three sides. So this is what we call as your volume or bulk stress, because it is a complete body stress that we are talking about. Okay. So this is the third stress that you know. So in this case, what happens? There will be change in volume. Okay, volume in the sense there is change in the length, height, and the thickness. Okay, so in this case there is only change in two dimensions. One is your length and then the width. The thickness may remains almost constant. Okay, in the first one there is change only in one dimension, other two is going to be constant. Okay, so then when it comes to strain, the same thing. It can be again longitudinal, which is your one dimension, and then shearing, which is your two dimension, shearing or tangential. Then last one is bulk or volume, which is your three dimension. Okay, so how do you define this strain? So stress is always force by area. Okay, so this we know, it is always force by area. In the first one we will have take the length for the area. In the second one we'll take the length and width. Okay, in the last one we have to take the entire volume, which is length into breadth into height. That is your area. Okay, so but the formula is almost same for all the case. Okay, so next, when it comes to your strain is defined as change in dimension by original dimension. Okay, so this is the very basic definition of strain. So this is the ratio of change in dimension to original dimension. So now in this case, what happens is, so if I take the longitudinal strain or linear strain, so in this case, or is some people also call it as tensile. Okay, so all names are same: longitudinal, linear, and tensile. Okay, so tensile means is also same as longitudinal or linear. Okay, so it is one dimensional strain. Okay, in this case. So now I take a rod. So this is a rod. I think you can see this, right? So this is a rod before you apply any. Okay, this top end is fixed. Then what I do is I will apply some load. So once you apply the load, what happens is this is again fixed. So there is a extension in the length, okay, which is in only one dimension. Okay, so for example, if I take the length before it was 1 millimeter or 1 meter, then so I will apply the load. Maybe it is 1.2 meters. Okay, and then I will remove the load. Okay, once you remove the load, what happens? It will go back, but it may not go back to its original length, which is 1 meter. It may come to 1.02 meters. Okay, so in that case, what happens is your delta L, the change the length will be 0.02 meters. Okay, so this is a change in length. So how do you define this longitudinal strain? Is it is the change in length by original length. So which is nothing but it is nothing but 0.02 meters uh, by 1 meter. Okay, meter will cancel, so it will be 0.02 meter, which is a dimensionless quantity. Okay, so whether you're talking about longitudinal or shear or bulk, all these strains are dimensionless. Okay, they don't have any dimension, which is they don't have any units. Okay, so in the second case, what happens? This is your shearing or tangential. Okay, so some people is call it as tangential strain. Okay, so in this case, what happens? You are fixing the lower end, and you are going to apply force on the upper end. So in this case, what happens? This A, B, C, D is if I take A, B, C, D as a point of your cube, then there will be the A is going to shift to A dash, B will shift to B dash, but C and H, so they will not move. Okay, so this is the displacement. And then once you remove the force, this A dash may not come exactly to this A, but it somewhere in the middle. Okay, so let us call this is the change in this position. Okay, so instead of what I will do is I will call this as A double dash, and then so if once I apply the force, A is coming to A dash. Okay, so now I will remove the force. Once I remove the force, then what happens? This point has to go back to A. Instead, what happens? It will stop at A dash, A double dash. Okay. So in that case, there is a small change in the delta L. Okay. So this is what we call as. So then we can take the shear angle or shearing strain as theta. Okay. So theta is the shearing strain or tangential strain. So this will be A dash by A. In our case now it becomes A double dash. Okay. A double dash by AD, and then theta will be delta L by H. So this is your tangential or shearing strain. So the last one is the bulk is what it is change in volume. Okay. So initially the volume was let us take it was V. Then there, if you apply the compress force, that is when you are compressing this, then the volume will shrink by a quantity of delta sorry dV. Okay. So dV is the change in the volume. Okay, so as it is decreasing, so I will put a negative sign, V minus dV. So if I take this volume of this sphere, then this should be dV. Okay, so now if I want to talk about the bulk strain, it is the same thing, change in dimension by original dimension. So in this case, the dimension is volume, so it is the change in volume by original volume. So then what happens? This will be dV by minus dV by d. Okay, so that will be the change in sorry your bulk or volume strain. Okay, so this is also called as volume strain. Okay? So now if I instead of this compressive, I can also have expansion. Okay, Chirag, you need to mute yourself. Okay, so instead of compressing this, what I can do is I can it out. Okay, from all the direction I can pull it out by applying the same constant force. So in that case, what happens? So from here, this volume would become somewhere here. Okay, so this would be the volume. So there is a increase in one volume. So during meditation, you can control this. Okay, and you don't try to share. By mistake you would have done, but don't do it because then my control will go up. Okay, okay, fine. So see, if I'm pulling this out, then it's a expansion. Okay, so instead of minus, there will be increase in the volume. So let us call dv is the increase in volume. So in that case, what happens? The bulk strain would be plus d by. So this is these things you need to keep in mind, okay, for your three with respect to your load and strain and stress. Okay, so I think we stopped here. So now there is one more thing which is I think this will come later. Okay, so you might know this Hooke's law. Okay, so I think you have already studied this Hooke's law. So what is Hooke's law? So within the elastic limit, okay, what is the meaning of elastic limit? So elastic limit means until your uh, keeps its elastic property, that is what we call as the elastic limit. Okay, within the elastic limit, the stress is directly proportional to strain, strain that is developed in the material. Okay, so in the material, so I think this I need to remove. Okay, so that is nothing but in okay. This has to, okay, stress is directly proportional to strain. Okay, so stress is directly proportional to strain. So then what happens? Stress is equal to E times strain, and E is called as your elastic modulus or modulus of. Okay, so this E, now what happens is it becomes as a ratio of stress by strain. Okay, so as we know, there are three different types of stress, and correspondingly there are three different types of strain. Okay, so this is what we learned yesterday. So what we do is we will, if I want to say some modulus, then again we'll have three different types of modulus. Okay, based on what kind of stress and strain we are applying. Okay, so this is what we are going to we are going to today. Okay, for today's class, we are going to study these three different moduli. Okay, so this is again you have studied in the previous class, so I'll just go a little bit quick. Okay, so modulus of elasticity or elastic modulus, there are three types. One is your Young's modulus, then you have your rigidity modulus and bulk modulus, or you can also call it as volume. Okay, so now if we will define one by one. Okay, so if I take the first one, which is your Young's modulus. So how do you define this Young's modulus? Young's modulus, it is nothing but it is a ratio of longitudinal stress to longitudinal strain material. So y is nothing but tensile or longitudinal stress divided by tensile or longitudinal strain. Okay. So this we already know what is longitudinal stress. Longitudinal stress is force by area, and what is longitudinal strain? It is nothing but delta change in length by original length. So this is what we did in the previous class. Okay. So hmm. Okay, so where is your tangent? Okay, so this is your tangential. Tangential is force by area. Tangential or longitudinal, sorry, not tangential. It is a tensile. Okay, tensile or linear stress is force by area. So same way, tensile or longitudinal strain is change in length by original length. So this is what we use here. Okay, so we use the same thing in this case. Okay, delta L by L. So I am keeping the same notations. Okay, from we will use, you can give any so you can also use small l, but when you use small l you should tell this is the length of the your rod. Okay, so or your wire, whatever you are using. Okay, So then the second one, which is this is your one dimensional one. So next you go for two dimensional. Two dimensional, it is shear or rigidity modulus. So it is related with your shear stress to shear strain, or what is the other name? What is the other name for shear stress or shear
Tangential.
tangential? Okay, so
Tangential
you can,
stress.
yes, yes, right. So you can write it as tangential stress by tangential strain. Okay, so you can use any one of. So there is no restriction that you have to use only shear or only tangential. Okay, so both are correct. So you can use any one of them. So this again, how do you define this? Is force. Your shear stress is force by area, F by A. Then your shear strain is given by your tan theta or your theta. Okay, theta is delta L by H. Okay, so then L and what is delta H. Okay, so for that, what you are supposed to do is you need to write this diagram. Okay, in your when you are explaining, you write this diagram. Then you should show, okay, this is your delta L and this is the H. Okay, then you get tan theta is delta L by H, or theta is delta L by H. Okay, so this is your rigidity uh, or your shear modulus. Then the last one is bulk modulus. So bulk modulus is related with the volume. Okay. So the ratio of volumetric, you can also use volumetric stress by to volumetric strain within the elastic limit. Okay. So you should always use this word. So you can see in all these definitions, I'm using this. Okay. If you don't use this, then there's this sentence or definition would be incomplete. Okay, the ratio of whatever you, so I think this is wrong, right? This has to be what? This has to be shear or tangential. Okay, so this is what happens if we copy paste. Okay, so this is your shear stress by shear stress and shear strain. Okay, not longitudinal. Okay, so the last one is your volumetric or bulk modulus. So this is nothing but it is the volume stress by volume strain, or you can also call it as bulk stress by bulk strain. Okay, so this is your bulk modulus. Okay, so these are the three different kinds of modulus. So these what is your modulus gives? What property of your material will your modulus give? Anyone knows? Because you guys should know. You guys will be using this a lot. Okay. So what is the meaning of the what is the use of this modulus? So we wrote here it is a elastic
To know
modulus.
strength of material, sir. To know strength of
Yes.
material.
Yes. So this is this it gives the strength of material. So you can decide whether this material is useful for your application or not. Okay. So based on the modulus, okay, you can use that material for different application. Okay. So this is why this is very important. So later during your maybe your fourth sem or fifth sem, you're going to have one complete paper only on strength of material. Okay, so that is why you need to know this, concepts. Okay, this is very useful for you in even in the higher semester. Okay, so now there is last one, which is your Poisson's ratio. Okay, so what is Poisson's ratio? Can anyone what is Poisson's ratio? So when I was explaining the longitudinal strain, okay, what I told was I am taking some material which is having very long length, okay. Then I told other two dimensions are very small, right? So in most of the case, this may not be the what is the situation, but what happens is you if you take some rod, okay, so if this is like 1 meter length, 1 meter length, and maybe this is around point or 0.5 meter diameter, okay. So this, in that case, what happens if I fix one end? So let us assume this end is fixed, and I am applying the force in the uh, lower part. Okay, so best example is you can take a rubber band. Okay, so just give me 1 minute. Okay, I will come. Okay, so maybe just So can you see this rubber? Okay, so you can see this rubber. What happens is this is having certain length, and you can see the thickness. Okay, so when I stretch this, so what happens to this? So when I stretch this, the length is increasing, right? But what happened to the thickness?
Decreasing.
So
Decreases.
decreasing, right? So if I stretch it more, then what happens? Almost like a line. So even though I told there is only one dimension change, okay. In this case, what is happening is there are change in two dimension, okay. So first one is there is a increase in the length is increasing. At the same time, what is happening is the diameter is going to decrease, okay. So so in this case, I cannot just tell there is only change in the length, okay. So maybe also change in diameter, okay. So I will apply the load and I will leave with this, okay. I will remove the load. When I remove the load, it has to regain its original dimension or diameter, right? But there may be some effect of the load. So there this diameter may decrease, okay. So in that case, what happens is okay. So in that case, what happens is you will have some change in the diameter. So this change in diameter we call it as lateral strain. Okay. So lateral strain is what this is similar to your longitudinal strain. So longitudinal strain is change in length by original length. In case of your lateral strain is change in diameter by original diameter. Okay. So this is your this is the second term. So using this, there is one more thing what we call as the Poisson's ratio. Okay. So along with these three modulus, okay, you have Young's modulus, bulk modulus, and also rigidity modulus. So along with these three modulus, you will also have something called as the Poisson's ratio. Okay, which is the ratio of lateral strain by longitudinal strain, which is change in diameter to the original diameter divided by change in length to original length. Okay, so then it becomes your Poisson's ratio sigma. Okay, we call it as sigma. Sigma is beta by alpha. Okay, beta is your lateral strain, alpha is your longitudinal strain. So we'll come back to this again. Okay, so beta by alpha. Then this will be equal to so delta D by capital D, or in is called as D naught. D naught is the original diameter divided by delta L, which is the change in length divided by original length. Okay, so here they are using small l, but you can also use capital L. Okay, so if you simplify, then it will your L will go up, and then it will be delta D into L divided by delta L into D, okay, or D into delta L, okay. So this is your Poisson's ratio, okay. So this is also very much important. So we are going to learn
Sir,
more on this in the next class. So yeah, you have some questions?
sir, minus delta d by d, no, sir.
Yes, minus because it is decreasing,
Radius
okay.
decreases.
Yeah, your meter is decreasing. So if whenever there is a decrease, you should use minus. Okay, this tells it is a decremental. Okay, so as I told, even in this case, so you can also have something called as a incremental. Okay, so if I for that what I am supposed to do is instead of applying the load along the length, I can also uh, apply the load along its diameter. Okay, I will just try to stretch it in this way. Okay, so in that case, what happens? The diameter is going to increase, but the length is going to decrease. Okay, because this is also possible. So, based on what direction you are applying the force, you can have decremental or incremental change in the diameter. Okay, so either you will get negative in the uh, numerator or in the denominator. Okay, so based on the direction of the applied force. Okay, so okay, fine. So if you have any questions, you can ask me. Do you have any questions? concept. So this concept is for your stress and strain diagram. Okay. So again,